The drop deadline's what, next week, like Monday night, I think. So just a reminder of what you need to do in the course. The prelim 2 reflection's up on Canvas, so if you didn't get that done during discussion today, please make sure to do that. Even if you're here right now, you still need to submit this for your notes page next week if you want to get credit for that. I haven't opened that assignment yet because I don't want anyone to think that's the one that's due tomorrow. It will be the one that's due next week. And then because the exam's on Tuesday, it's really hard to get good attendance at the discussion section. So for prelim 2, I won't have any discussions. Prelim 3, way in November, I will actually have the discussions there because we're so close to the end of the semester that starting the review still makes some sense. So no discussions next week in 1057. Really, we'll start with some nomenclature. Remember, nomenclature is not going to be the main emphasis of the exam, right? You kind of saw that in prelim 1, but I wouldn't be shocked if you had maybe like 10 or so points. Remember, where that's coming from here is also R and S nomenclature and the new bicyclic stuff. So I have 2 examples of that here. If you haven't watched the video where I think I gave another 4 examples to practice with. I think those are good ones, and really students tend to be okay with them once you get the practice with the bicyclo stuff. But I would say somewhere between 8 and 10 points, maybe doing R and S, either drawing or naming the compound, and then either drawing or naming your bicyclic system. Make sure now the added part. This looks like you probably could name this way back on prelim 1, but the dashes and wedges is what adds our new complexity to these. So I'm indicating that those are asymmetric carbons. I would want to go ahead and prioritize, rank my 4 groups. And so in this case, to start, my chlorine's 1, my carbon to the right is going to be 2, my methyl group is 3, and my implied hydrogen is 4. That's going away from me. So I don't actually label my 4th here if my hydrogen's not shown, but I can tell that my 4th group is going away. That means I can go ahead and rank these, draw my clock. These are going to be R. Next one, same idea. Let's go ahead and rank. The chlorine will be 1. Now, when I'm looking at this position here, this carbon has only 1 hydrogen. This has 2. So that means this is going to be my 2nd priority, my 3rd priority. And again, the hydrogen that's implied there is going away. So now I can go ahead and connect. That's also going to be R. Now I need to use my old alkane nomenclature rules. So I have a chlorine on position 2, a chlorine on position 3. I have the 2 position being R, the 3 position being R. If I put that all together, brackets, 2R, 3R. Here's my dash, 2, 3, dichloropentane. So the second half of this should all feel familiar from prelim 1. The only added piece is now making sure I assign the asymmetric carbons at each position. Since there's 2, you need the numbers here. So I need to have 2R, 3R. If there was a compound that only had 1 asymmetric center, then it's obvious where that letter should be, and you don't need the number, but you're welcome to include it if you want. Next one, this is an example of our spiro rings where we had 1 atom that's participating in both of my rings. So the first part of this would be recognizing this as a spiro ring. Then I'm going to go in both directions from that single carbon that's in both. So from here, I have 1, 2, 3, 4 carbons. From here, I have 1, 2, 3. I'm going to write those from highest to lowest. So I have a spiro, brackets, 4-3, end brackets, total number of carbons. So I have 1, 2, 3, 4, 5, 6, 7, 8. I think some sources have it, may say it doesn't matter. Everything he showed in class was going highest to lowest. I think that maybe there's a newer updated version where they say it doesn't matter, but everything I can see that goes from highest to lowest. So I think that would be the best answer. Next one, same idea, right? So I see my asymmetric centers. We're going to go ahead and assign R and S here. So my bromine would be position 1. here would be position 2. The reason why this pathway is position 2, these two carbons are the same. They both have 2 H's and 1 carbon. But now this carbon only has 1 H, so this pathway is going to be a higher priority than this pathway. My 4th priority is my hydrogen, also going away from me, so I can just go ahead and connect my 1, 2, and 3. That makes this one R. For my other asymmetric center here, for my numbers, right, this is going to be 1 because this pathway has the bromine before this pathway. This is going to be 2 because this carbon has 2 hydrogens and a carbon, whereas my methyl group only has 3 hydrogens. In this case, my hydrogen is coming towards me, which is the opposite direction we want our 4th priority to be pointing. So what I would do here is I'm seeing that this is counterclockwise. This is S, but because my hydrogen's in the opposite perspective, I need the opposite letter. So this is also R. Now when I piece this together, right, so this is another kind of our tiebreaker rules from Prelim 1, where we have our substituents. They are going to be at positions 1 and 3, no matter what we do. We need to decide, would we rather have the bromine be carbon 1 or the methyl group be carbon 1? Since bromine is going to be first in our name based on alphabetical order, we're going to number that at the 1 position. So I have a brackets or parentheses, 1R, 3R. That tells me the positions of the bromine and the methyl, what their configurations are. End parentheses, dash 1 dash bromo, dash 3 dash methyl, and then remember the cyclohexane part. I saw a few mistakes on Prelim 1 trying to add cyclo when we didn't need it. I'd say this is a pretty common one now because we did chairs, we did cyclohexanes in chapter 7, right? So I think that being able to be prepared for a ring compound with your asymmetric centers or a linear one is fair game. But just to highlight, remember, if there's a circular system there or a ring system, you add that cyclo to your D. Last one here, these 2 carbons are our bridgehead carbons. So here, this isn't spiro because spiro has 1 carbon that participates in both rings. In this case, we have 2 bridgeheads. Both of those carbons participate in both rings. So this is going to be my bicyclo to start. Now I'm going to number 1, 2, 3 carbons in one direction. 1 carbon in order to get back to my other bridgehead. So bridgehead, 1 carbon, bridgehead. Bridgehead, 1 carbon, bridgehead. So bicyclo, and then highest to lowest, I have 3 carbons, 1 carbon bridge on the right, and another 1 carbon bridge on the left. The numbers, I've always seen them in the middle. I've never seen them at the end. Sort of similar to our traditional principal chain.
Can you explain why the 3rd carbon is an R?
In this one?
Yeah.
So this is, are you okay with my priorities? Because the 4th priority is coming towards me, we normally need our 4th priority going away from me. So if that's hard to remember to switch, you can redraw this where you would draw the enantiomer, where the methyl group would be coming towards you and the hydrogen would be going away. But I just know that if my hydrogen's in the opposite perspective, or really I should generalize that and say if my 4th priority is in the opposite perspective, that means that whatever letter I see, it needs to be the opposite configuration.
Thank you.
So hopefully I'm not stressing you out too much with these. I wanted to give you some straightforward examples with the bicycle. I didn't see any. Did anyone get through the homework? I didn't see any of these in there, but I went through it pretty quickly. So if you haven't tried more of these, definitely check out the video for some more practice with these. Okay, I think these are actually easy points, but they look a little scary. So I'm trying to push that video a little more than usual because I think you can get them.
Sorry, can you go over the numbering at the flip bicycle again?
This one?
Yes.
So my bridgeheads would be the 2 carbons that are part of both rings, right? So my 2 rings are this flat one, this flat chair, and then now this chair that's sort of pointed up here. So in order to get from this bridgehead to this bridgehead, we have 1, 2, 3 carbons. That's that 3. In order to get from bridgehead to bridgehead this direction, there's one carbon. And then lastly, in order to get from bridgehead to bridgehead, we have this one carbon. Okay. Any other nomenclature questions? Take-home message here would be, right, I care way more about the practice with the R and S, right, and the bicyclo ones, just because if they're on there, I'm not saying you'll definitely get them, but make sure you're comfortable with that procedure. Some more R and S practice. So I think I'm going to go ahead and assign priorities here. If you wanted more practice with these, I'll go through this part pretty quickly. So priorities, oxygen would be number 1. My carbon here has only 1 H. This carbon has 2 H's, so that's why my priority is 2 and 3 here. In this case, again, my 4th priority is coming towards me. So this is the opposite perspective of what I need. So whatever letter I see, I'm going to flip. So this looks like it would be R, but my H is in the opposite perspective, so this is S. For the bottom one here, my hydrogen is going away from me, so my 4th priority is going away. That's where I want it to be. Let's go ahead and rank. I have my nitrogen beating out a carbon. I then have a carbon here with 1 hydrogen. I then have a carbon here with 2 hydrogens, so that means this is going to be pathway or priority 2. This is going to be priority 3. Now, again, my H or my 4th group is going away, so I can go ahead and connect 1, 2 to 3. So this one's also S. Make sure that when you're classifying your asymmetric carbons, that you need 4 groups, right? So if you get to a position where you don't have 4 different groups or you can't rank 1 through 4, you're not going to be able to assign R and S. So in this case here, I'm trying to show this example where I have 2 of the exact same groups. There's no way to decide which one's 3, which one's 4. This is not an asymmetric center. So I would write neither N for neither or not an asymmetric center. I think these 2 are the way more common cases. I wanted to give one more example, and we'll have more practice of this if you're having trouble. But when I go ahead and assign priorities here, so bromine is lower on the periodic table. That's going to be 1. I'm comparing carbons to chlorine. So chlorine is 2. And then when I'm looking at my carbon groups, I have a carbon here with no hydrogens. I have a carbon here with 2 hydrogens. So my 4th priority here is in the plane of the board. My advice or strategy for how to handle this is to redraw this, and you can either rotate like I talked about in my video, or you can do the switch 2 groups that Dr. Ganem talked about. So what I would draw here would be the exact same molecule, and rather than worry about, well, hey, this is a carbon with methyl groups, this is a carbon with 2 hydrogens, what I really care about in order to assign R and S is I need my priorities. So if I ever have to rotate, I'm not really worried about what the groups are. I'm worried about where my ranking is. So what I would do here is this group is number 4. I would redraw this with 4 and 1 being switched. Okay, in order to get to my enantiomer and to get to a way where I can see my 4th priority group is now going away from me. If you're really good at visualization, remember the other option would be, if you don't want to redraw it, your goal would sort of be to look dead on onto this bond where your 4th priority is going away from you. If you can visualize that Newman projection, great. That's the goal, but if you can't, here's what I would draw, where my 2 and my 3 groups have stayed the same. My 1 and my 4 groups have switched spots. Now my 4th priority is going away like I want it to in order to assign. And this looks R, connecting 1 to 2 to 3, but I switch those 2 groups. So if I'm seeing R, that means before I switched, it has to be S. Okay, so I would say, especially in these cyclic structures or any time you have to redraw, I really don't care what the groups are. I care about my ranking. So that's why I redrew this with my 2 and 3 groups in the exact same spots. I switched my 4th priority with whatever was on the bond that was going away. All right, so it's not like I need to switch 4 and 1. It's that I need to switch 4 with whatever group is going away from me. That way I can easily assign and connect 1 to 2 to 3. If you're having a lot of trouble visualizing this, I really recommend redrawing it this way. But this is, again, the hardest case scenario where you're going to have to be able to see it because this is the 4th in the plane of the board or in the ring in the plane of the board. So I think that just makes this one a little bit harder. But if you're getting these, I think you're in a good spot. Okay? Any questions at all on RNS?
For the top one, would you prioritize CH over CHH if one had less height?
Yeah, I mean, to me, this one.
Yeah.
So this is CH, really, right? The other 2 bonds. This is CH. No, it's double bonded, so you count the 2 C's. That goes back to E and Z. All good on this one? At least some strategies. There is another example of this, actually number 4, the next one that's coming up, more practice with RNS. Okay. Okay, next one. So I tried to draw these and give you a couple different examples. Usually every Prelim 2 with every professor I can think of, they try to trick you with one example where they want it to look like it's an asymmetric carbon, but it's going to have 2 of the same groups on it. And that's what I did in this first one. So I think there was one in the homework where they actually did like a CH3 here and then didn't label the other position. Remember, these are both CH3s. And so if those are 2 CH3s on the same asymmetric carbon, we're again stuck in the same situation where I can't rank 1 through 4, so I can't assign RNS here. So this is not an asymmetric center, even though I'm drawing the dashes and wedge, because this is a methyl, this is a methyl. When I redraw this, I'm going to be able to get the exact same molecule. I did it again on the other position as well. So this is a CH3, this is a CH3, so neither of these positions are asymmetric centers. And so that's why this one would be achiral. For the next one, I think somebody, oh, go ahead.
Sorry, I just don't understand the reasoning. What is it? What does the 2 CH3s have to do with it not being symmetric?
So it's not an asymmetric carbon because it doesn't have 4 different groups attached to it. So if I try to assign priorities here, I know the bromine would be 1, and this group, because this has no hydrogens, this would be 2. But if these 2 are the same, there's no way to say which one's 3, which one's 4. If I can't assign RNS to it, then it's not an asymmetric carbon. For the next one, right? So I think in class, Dr. Gannon made a big, oh, sorry, go ahead. No questions on the first one?
Yeah, just to clarify, so for a carbon to be asymmetric, there has to be 4 different groups attached to it.
Correct. Yes. And I'm not saying atoms, right? Because you can have 2 carbons, but one carbon's got to be a methyl, one's got to be an ethyl, right? So I'm saying groups there to just say that I don't want to say atoms because you could have 2 different carbon groups.
Yeah, so if there's no asymmetric centers, does that automatically make it achiral?
For our purposes, I want to say yes to that. There's a section in the book that Dr. Dan can go into where that's not always the case, but he kind of skipped it. It's called axial chirality. There are some examples you might remember from Gen Chem looking at axial and equatorial groups in your Lewis structures. So I don't want to overcomplicate things like that, but since he didn't talk about that, that should be your answer.
So the first one was achiral.
Correct. So in lecture, I think Dr. Gannon was really relying on you being able to kind of see mirror images or rotate bonds in your head. As a sophomore, when I took organic, that was really hard for me to do. And that's why I emphasize assigning RNS so much, because if you can't see the rotation and see the molecules, RNS doesn't lie. So for this next one, this is actually very similar to one on your homework. This next one is a meso compound. And not that you need to memorize this template, but how I would identify a meso compound would be, let's assign RNS, and then let's draw its mirror image and assign RNS again. The goal of this, right, is if you draw the mirror image of something and it's identical, then it's achiral. So how I would do this one, again, this takes time, but I think it makes more sense to do this than trying to like, hurt yourself or overthink trying to do this rotation. I just couldn't get it when I took it organic the first time. So if you're having trouble doing that and seeing how these are going to end up being the same in the mirror image, let's do RNS to see that. So I'm going to redraw this. I'll do quick priorities here. I'm not going to go through and assign why these are 1, 2, and 3, but I'll say that this is now R, 1, 2, and 3. This is now S. So now I'd want to draw its mirror image. That's what that mirror image would look like. So if I had my mirror plane here, and I would say at this point, even if you can't do the rotations, flipping things over really well, what I'd want you to see is that when this is the mirror image, it's that my 2 and 3 priorities have switched sides. So whatever letter this is, it's going to have to flip because 1, 2, and 3 are going to go in the opposite direction. So I would hope you'll be able to see that. If you can't, you can still rank, prioritize, connect 1, 2, and 3, and you'll see that that ends up being R now. For my next one, let's do the same thing. 1, 2, and 3, S. So if I look at my molecule, right, this is where I think nomenclature kind of helps you a little bit, is that if I number in this direction, I have my first chlorine carbon as R, my second one is S. If I look at my mirror image, the first carbon is R, the second one is S. This is the case where my mirror image is identical because the 2 asymmetric carbons are connected to the exact same 4 groups. Already a hint for this last one. Okay, so I will say if you're having trouble trying to rotate, see the mirror images, RNS is the foolproof way. You might have to get a little faster at it, looking at priorities, but it will always give you the right answer regardless of how well you can see the rotations or see the mirror images.
Would it be fair to assume that this applies to every instance? So like if you were to flip the mirror image and the carbon RNS configuration still aligned, like
This is achiral because it's the same. That's why, so like I think meso compounds are the most confusing topic in chapter 7, and they're this really small subset because before you even consider mirror images, or sorry, meso compounds, you need to have the same connections on the same 4 groups, right? That's a blanket statement. If in this last one, I'm kind of going a little ahead of myself, but these 2 asymmetric centers are not connected to the same 4 groups. That cannot be a meso compound. I have no planes of symmetry there. When I draw this mirror image, right, I won't go through and assign R and S, but they're going to flip, and now I won't be able to have the same compound because the carbon with the bromine is going to have the opposite letter. The carbon with the chlorine is going to have the opposite letter. So I think like these meso compounds are almost like these small exceptions. And if you can eliminate those, really you're deciding enantiomers, diastereomers, and R and S you kind of need in order to pair those up together anyway. And so I think R and S really is the safest way to make sure you're getting these, even if you can't rotate or see 3D. So that means this mirror image is identical. That makes this one also achiral. This one, I threw this in here just to try to make sure you can see some of the planes of symmetry. If I cut this molecule in half right down this line, I can fold it in half. Everything matches up. I always think of those pop-up greeting cards, right? Everything, when you fold it, should be identical. So this one, because I have a plane of symmetry, even though I have asymmetric carbons, this one is achiral. Now I no longer have that plane of symmetry. This one is chiral. So I can fold this one in half right down the center. I cannot fold this one in half. And if that plane of symmetry is hard for you to see, assign R and S, draw the mirror image, and assign R and S again. You'll see that that one will not match up. For my last one here, we kind of already talked about it with this one, right? So when they have the same four groups, if they're opposite configurations, they'll be meso. In this case, they do not have the same four groups. That means these two asymmetric centers are different. So that mirror image is not going to be identical, which means that one's also chiral. So two things here. Any of those tripped you up, right? This is the exercise I'd want you to do. Draw it, assign RNS, draw the mirror image, and see if you have the same molecule or different. Okay? Bottom one here, right? If I'm just looking for asymmetric carbons, I'm looking for carbons that have four groups. I think the easiest way to kind of hone in on specific carbons for this question is to look at any carbon that only has one H. If it has two H's, it's not going to have four different groups. So I would start up here, this alcohol group here, right? There's one hydrogen there. I can see that this pathway and this pathway are different, so I know that's going to be an asymmetric carbon. For this one, I again have one hydrogen here. I have an oxygen, a CH2 that's part of a ring, and I have a CH2 that's not part of a ring. So that's another asymmetric carbon. If I look at this position, that also has one hydrogen. So that's going to end up, I'm saying that this has a CH group, a CH2 that's not part of the ring, and a CH that is part of a ring. And so that's another one. Same thing here. So I have a hydrogen at this position, a C that's part of an alkene, a C that's not, and a methyl. If I go to this position, 1H, three different carbon groups, a carbon that's connected to an oxygen, a carbon that's not connected to the ring, and a carbon that's in an alkene. So this is another one. The other thing we're looking for, remember, for our asymmetric carbons, you need to have sp3 hybridization. So I'm also eliminating anything where I see sp2 hybridization, like from my alkenes here. I got three more. Here again, one hydrogen. Here again, one hydrogen. And then the last one's going to be right here, one hydrogen at that position. So I would go ahead and draw in your H's at that point if that's tricky, but this is kind of just making sure you can identify your number of asymmetric carbons. And then the other thing in discussion this week, I saw a lot of students forgetting that formula. So remember that 2 to the n telling you the total possible stereoisomers. I don't think he would make you do that math here, but 1, 2, 3, 4, 5, 6, 7, 8, 2 to the 8th, that would be my total number of stereoisomers or possible stereoisomers. So that formula also is something you want to remember. It depends on the question. For if it's saying, if is it chiral, I would. In the next question, I give you two structures, and then I wouldn't draw the mirror image of those. I would just assign RNS. Does that make sense? But if they're asking me if something's chiral or not, I would. And I'll say that's not the way, you don't have to do it. So some of you are actually better at the visualization than me. I've gotten a little better at it since I was a sophomore, but I'm still not as great. I like to think it's because you guys have been on iPads and playing video games and seeing things in 3D way more of your life than I was when I was a sophomore. But that's the best way I could say in order for me to get the answers, I had to draw the mirror image. But I would say it's about 50-50 in the students I work with. Some of them don't need to do that in order to see.
So when you draw the mirror image and they're the same, that means that they are achiral?
Correct. So non-superimposable mirror image would be chiral. A superimposable mirror image would be achiral. Okay. So I really like these style questions because it kind of gives you a wide net of different ways he can ask this. This style question wasn't on any of the two practice exams, but I have seen it used on previous 3570 exams with potentially different professors. And so I like this style just to give you some different examples of these. And I want to sort of talk my mindset. So sometimes, like I said, I can't really see the rotations. Sometimes I can. And if you want to assign RNS in all these cases, you absolutely can do that. but I want to point out some of the other tricks I use to kind of save time a little bit. So in this first one, right, I can see that whether this position is R or S, I don't really care because it didn't change. In this carbon, I don't care whether this is R and S, but I can see that it did change. So right away, let's go ahead and say this is R. I'm not sure if it is. Let's say it's R. That means this is R. Let's say this is R. That means this is S, right? And you could go and assign R and S, but for me, I can see that some of my asymmetric centers are the same, some are different. That means that these are diastereomers. And you can prove that with assigning priorities, but the idea for me is that, hey, doesn't matter whether that top position is R and S. It's not going to tell me the difference between these two molecules. It doesn't matter whether this position's R or S. I know that it's changed. It is going to tell me the difference between those two. Next one. I think this one looks scary. I think there was maybe one on the homework that made you do this. Did anyone get to that one yet? I thought there was one on the homework that's like this. If this looks scary, what I would encourage you to do is first count your carbons. Make sure you have the same number of carbons, right? If you have different number of carbons, then that kind of gives it away. But how I would do this one without assigning R and S, right? It's really hard to assign R and S to a Newman projection. You could, but you're going to have to redraw it. Tell me which bonds are wedged and dashed, and then assign R and S, right? But what I would do here is look at my anti-relationships. So my chlorines are in opposite directions. My chlorines, opposite directions. My hydrogens, opposite directions. Well, my hydrogen at this position is on a dash. My hydrogen at this position is on a wedge. My methyl groups opposite each other, those are anti. My methyl groups should be going in opposite directions. One methyl group's down, one methyl group's up. So without assigning R and S, without redrawing, I can see the relationship for each of these is the same as they are in this one. That means these are identical. All I'm doing is saying which bonds are opposite each other in this structure, which bonds are opposite each other in this structure. Next one. So here's where we have two strategies. Depending on how well you are with the rotation and the flipping, that would be the fastest way to do this, right? So I'm going to try to attempt to show you how I would visualize that. What I would want to try to do is see if there's a way I can turn the right-hand molecule into the left one. So the first thing I would do is let's twist this and rotate to get the methyl group and the bromine on the right-hand side. If I twist enough to the right, I'd end up getting that structure. Can everyone see how I did that? I just took it, twisted it over so that my methyl group and bromine were on the other side. I didn't flip it over. I just twisted it. Now, if I take this and flip it up like this, my methyl and my bromine would be in the exact same spots, but now they would be opposite orientation. Because when I flip this over, my methyl group that was coming towards me would be in this position, but it would be going away from me. The bromine that was going away from me would be in this position, but it was coming towards me. That's how you would be able to rotate and see that those are not identical. Those are opposite configuration at each position. So these are enantiomers. If that rotation was hard to do, right? R and S. So I'll go through the priorities really quickly here, but in this first one, that methyl group's going to end up being R. In the second one, that bromine is going to end up being R. When I go to this one, my methyl group here is going to end up being S. So my methyl group went from R to S. For my bottom one here, 1, 2 to 3, that's going to end up being S. Remember, this one's going to flip because the hydrogen's going away from you. And so now it's a little bit easier for me to see that R to S, R to S. And so that is enantiomers. So that's what I mean about the two strategies, right? If that rotation is going to be problematic for you, RNS is going to still get you the right answer. It might take a little bit longer, but I find rather than stressing students out about forcing you to see that rotation, this is the second strategy. Last one. This is where another application of where nomenclature I think helps me see things better. If I were to go ahead and number this molecule on the left for where those methyl groups are, I'd want to start here. This would be position 1, 2, 3, 4. So I have 3 methyl groups on 1, 2, and 4. For this one, I have 3 methyl groups on 1, 3, and 5. Without having to worry about RNS, those methyl groups are not on the same carbons. They are connected differently. So these are not stereoisomers, they are constitutional isomers. Now, you could go ahead and assign RNS if you wanted to here, but that's not going to help you compare them because in order for you to assign and compare RNS, they have to be stereoisomers. If they're not connected the same way, that information isn't relevant when you're comparing. Any questions on any of these 4? Okay. So again, for this one, right? This is why I threw this one in here. Just different representations. So you actually could, if you wanted to try to rotate these, see if you could flip it over. But what I would do in this case, if that's hard, let's go ahead and rank priorities. This one with the chlorine is going to be R. The fluorine's going to, or the carbon where the fluorine is going to end up being S. Now when I get to this one, the carbon where the chlorine is going to be R. The carbon where the fluorine is going to end up being S. So I drew those in different orientations, but by doing that, I actually didn't change the asymmetric center configuration. So the carbon where the fluorines are, the carbon where the fluorines S, the exact same configurations are on those positions. So these are also identical. If you're feeling the RNS is taking up too much time and you're worried about time on the exam, right? Remember that when I switch one thing, I get to the enantiomer. If I switch 2, I'm back where I started. So why I say that is that I switched the fluorine and I switched the direction of where the chlorine was. So I switched 2 things. Switching 1 would get to the enantiomer. Switching 2, I'm back to the origin. That's hard to visualize. RNS did not fail me here. Okay. Next one, you think I would assign RNS in order to match these? Same strategy as I did in that first one, right? Remember, I didn't care what the configuration is. It's not asking me to assign RNS. It's saying, what's the relationship here? So I'd say whatever the configuration is at this position, it's switched. Whatever the configuration at this position, it's switched. Both of those switched. Those are enantiomers. And I didn't do it here, but if you wanted to assign priorities and RNS, you'll also be able to see that as well. But fast way, if I'm switching one group at a position at a specific carbon, that's going to give me the enantiomer. I always like to throw this one in here. This one's a little tricky because I don't have any asymmetric centers to look at. I can't assign RNS to that. So let's look at our options. Well, if I don't have any RNS, I would say, let me draw these. Are these mirror images of each other? No way, right? There's no way these are mirror images because the bromine's pointing in the opposite direction. So what can I eliminate already? If they're not mirror images, then they can't be what? They can't be enantiomers. Are they connected to the same atom? So meaning both carbons in my alkene, are those connected to the same 3 groups? Yeah, right? So my carbon on the left here, that's double bonded to a carbon. it's bonded to a hydrogen and a bromine. Carbon on the right here, double bonded to a carbon, a bromine, and a hydrogen. Carbon on the right here, a methyl group, a hydrogen, double bonded. So these also can't be constitutional isomers. They are connected in the exact same way, or connected to the exact same groups. I also know these are not identical, right? And so that enantiomer diastereomer, remember, the enantiomers are also a tiny sliver because you need everything to be opposite. By process of elimination, you can get to that these are diastereomers, right? If that's hard, let's also go back and think about what this definition is, right? These are non-mirror image stereoisomers. Well, that fits cis and trans exactly. Those are non-mirror images, but they are connected to the same groups. And so our cis and trans alkenes are going to be diastereomers, but you can get there two different ways. Yeah.
Is that like a general?
I'm wanting to go back to U because I'm seeing that it just looks like different to me.
For, I guess it would be the first carbon, right? In red. So this carbon is connected to a methyl group, a carbon that has a fluorine and an ethyl group on it, and a hydrogen. Yeah, so I just switched which bonds were there, but they are the same groups. I also would say maybe adding the CH3 to that position might make that a little easier. Drawing in your H's might also make that a little easier to see. Last one for this one, I threw this in here just to give you another opportunity to try to rotate or switch groups. So you can kind of see on the one on the right, my hydrogen's in the plane of the board. So I would either do my rotation or I would switch two groups. So I showed the switching two groups one earlier. For this one, I'll assign priorities. That is S. Here, it's a little harder for me to see that. Remember, if you're able to take that bond, swing it towards you, and make your Newman projection, great. If you can't do that, let's rotate the molecule in order to get that fourth priority on the bond going away. So what I did in order to do that, right, so is in the plane of the board, so my hydrogen would be in white. I held my methyl group and then twisted it to get my white group to be going away from me. Now I didn't break any bonds, I just kind of rotated my perspective. So whatever I see when I rank here, that is going to be my configuration. I don't need to worry about switching anything like I did with the other method. That means that when I connect 1 to 2 to 3, that is also going to be S. So that means these are identical.
Again.
Which part? Yeah, so you're okay with the first one, how I assigned? Yeah, the H is coming towards me, so I have to flip that one. So what I did here, remember your two possibilities. You can just switch the two groups, switch your fourth group with whatever is going away from you. I think that's a little annoying because you have to remember to flip the letter back. So what I would do here would be to actually rotate my fourth group to make it go away from me. So my hydrogen in this case, if I start here, my hydrogen's in the plane of the board. If I twist this that way, my hydrogen's going away from it. So
Okay.
all I'm doing is spinning the other three bonds like a top until I get my fourth priority in the spot I want it to be. Since I didn't redraw it, I didn't disconnect anything, I don't need to worry about switching my letter. So all I did was sort of change my perspective. It's just that I think it's an easier way than trying to do the Newman projection where you're taking that bond and looking at it that way.
Yeah.
You're basically twisting it to get that group away from you. And since you're not changing the molecule, whatever you see is R and S, R or S.
So that I don't have to paint the wedge, right?
Correct.
It just has.
The lowest has to be the dash. Everything else okay with that one? And I would say the one thing in talking to students about their scores on Prelim 1 or question styles on Prelim 1, right? This is a multiple choice question. So if you can eliminate some specific options, that does make this easier. So even if you weren't sure about G, right? For me, I would say they definitely aren't identical, and they definitely aren't enantiomers. So you're really down to, well, are they diastereomers or are they constitutional, right? Like you can kind of go process of elimination if you know those definitions.
So for the enantiomers, every R has to switch to S and every S has to switch to R.
Mm-hmm. Opposite configuration at each asymmetric center. I thought there was a hand over here.
The different like the chronology, like we would first like determine whether it has 4 different groups, but like in this case it's a constant. So like why does it like break that rule?
These, so really remember, we're not comparing these as mirror images, it's whether the mirror image of itself would be a different compound or not. And so if you draw the mirror image of the cis or trans, it is identical. So I'm not saying either of these are chiral. So that's really why, but diastereomers do not have to be chiral, right? So that's where you can have the pairs, what we worked on today, where you have meso compounds and you have a pair of enantiomers, right? So that not everything needs to be chiral in order to make that relationship.
You said switch the lowest priority group with whatever's going away.
Mm-hmm. That's one strategy. That's not what I did here. I did the rotation. If that works, great. Some students are like, I don't like it because I have to remember to switch it and then switch back. So if you rotate, you don't have to worry about switching it again. Okay. So if you didn't watch my stereochem video, I give the 2 ways I think about these, but some students like the switching method, some students like this because it kind of helps with 3D and you don't have to remember to alternate the letter. I feel like most students, if they make mistakes in RNS, it's been, at least this week, it's been because they forgot to switch it. So that's why I like this method, because it doesn't ever allow you to forget to switch back. Okay. I did want to throw some of these in there, just being able to remind you of the equations that we need to remember. So our enantiomeric excess, this is our major enantiomer minus the minor enantiomer. In this question, it's telling me the S isomer is in excess, so it's telling me that the major has to be S, the minor has to be R, and the difference between those is 72%. The other way I would think about this, right, is this is the difference between those two, but it also tells me that whatever the difference is, that 28% has to be racemic. Because my excess is going to cancel out some of my S with some of my R. So I know I have an excess of 72% for my S enantiomer. The other 28% is canceled out. So that means that of my 28%, I have 14% S and 14% R. These cancel each other out. So the excess would end up being 72. So what I'd want to end up doing would be adding my 14% of my S that canceled out my R to the 72% of my excess in order to get the percentages of each. This one's nice because you can always double check this with your numbers, right? If this is correct, 86 minus 14 should give me my EE. So when you're calculating anything with an enantiomeric excess, remember that's telling you how much extra you have of one enantiomer. The rest of that percentage is going to be racemic, which you want to split between the two enantiomers. Bottom one, our optical activity equation. So remembering, oh, there's my 86 and 14. Remembering my observed rotation equaling my specific rotation times the concentration times the path length. I think this is completely fair game. The numbers would have to be nice and easy. So I think your homework might have given you some ones with some crazy numbers where you needed a calculator. I have seen questions like this on prelims before, and they've been numbers like a fifth, a fourth, a half that you should be able to work in your head. So as a reminder for this one, right? So In this case, we're looking for the specific rotation. That's going to be the one in brackets. So my alpha here that's not in brackets, that's the observed rotation. Counterclockwise direction, that's going to end up making it go in the negative direction. You do need to remember that. So that tells me that my observed rotation is going to be -2. My concentration is going to be my grams over milliliters. So 4/20 is going to end up being 0.2, a fifth. And my path length needs to be in decameters, which it already is. So I'm going to put those numbers in. I'm looking for the specific. So if I simplify that, I'm going to end up getting my specific rotation to be -5. So that's the kind of math I mean, but sort of mental math, maybe decimals, fractions are tricky a little bit, but that's the kind of question I think would be fair game with that formula. Okay. On to reactions. So strategies for predicting starting materials. I think right now, right, maybe you're looking at this and saying, oh, there's a lot of reactions. And that's true. Chapter 4 and 5, we're looking at maybe like 10, 11, 12 reactions. But right now, you really only know reactions for alkenes and alkynes. So if you can narrow it down to an alkene or an alkyne reaction, that's half the battle. If I have H2 with Lindlar's, is that an alkene or an alkyne reaction? When do I want to use Lindlar's? That's an alkyne reaction. So if this is alkyne, I know that I'm looking for where the alkene is. That's the position that was originally my triple bond. So recognizing your reactions, and maybe some are both, right? Actually, coming up, there's going to be one where it's alkenes or alkynes. But for this one, Lindlar's, that's specifically an alkyne reaction. So we'd only need to consider one functional group. Next one, ozonolysis. Alkyne or alkene reaction? Alkene. So I know I'm looking at making a double bond here. The next thing I would do is remember that step 2 here, that's the reagent that turns aldehydes into carboxylic acids. So what I'd want to do working backwards would say that before I do step 2, I would have both of those positions be aldehydes. Get those oxygens away. I don't want those to be in my starting material. Those oxygens are coming from my workup in step 2. Now that I see my 2 aldehydes, I think it's a little easier to see which 2 carbons are connected. So my carbon that has a double bond O here is going to need to be connected to the carbon that has the double bond O here. How I would do this to make sure I don't lose any carbons, I'd label. So this is known as mapping your carbons. I'm going to go ahead. Doesn't matter where I put as 1, right? It's just a placeholder for me. So if this is carbon 1, I'm going to say that's 2, 3, 4, 5, and 6. Now when I draw my structure, it's going to be easier for me to say, well, wait, I now have a 6-membered ring, and the double bond is going to be explicitly connecting carbons 1 and carbon 6. So my structure would end up looking something like this. I'm going to relabel my carbons to make sure I didn't drop any out. So carbon 1 and carbon 6 are going to be where my alkene is. Next one, BH3 and THF. Does that signal I have an alkene, alkyne, or both? BH3 and THF is for alkenes. The next thing I would think about is, do I have a Markovnikov or anti-Markovnikov addition? If boron is in step 1, is that anti or Markovnikov? Anti-Markovnikov, how I'm remembering that is boron in step 1, boron backwards, anti. That means that in my alkene, I want to have the carbon on the end participate in my double bond. And that means I only have really one possibility here, right? Because if I want that carbon to be involved in the double bond, this would be the only possibility in order to make sure that my less substituted position has, or is where my OH ends up. So any questions on strategies with those? First, identify your functional groups, draw all the possibilities, and then narrow it down to make sure that the answer fits your possible starting material. For anti-Markovnikov, this is straightforward. I only have one possible alkene. For Markovnikov, I might have 2, right? And then you're going to need to say, well, did my group go to the more substituted position, or did it go to the less substituted position based on your options? But this really is important to think functional group and go on from there. Everyone okay with these 3? Okay. And now for this one, H2 with PDC. Is that for alkenes, alkynes, or both? This is hydrogenation. This is for both. Remember we said H2 with Lindlars, that was only alkynes. If we don't have Lindlars, we can reduce either alkenes or alkanes. Sorry, alkenes or alkynes. So now this is where I'm sort of maybe doing some scratch work. I have extra space here, being able to say, well, if I have alkenes and alkynes, let me draw out all the possibilities, right? So I think the easiest one to start with is, let's add the double bond on the end here. That's possible. Let's add the double bond in the middle here. Now for this top one, do I have this double bond being EZ or neither? Remember, so Prelim 1 topic, I got 2 H's there.
Neither.
I don't have a higher or lower priority. This double bond's neither. How about the way I drew this one? Is this one EZ or neither? This is Z. That means another possibility would be E. What if I thought about this one? Are the top and bottom ones, let's get rid of these H's. Are these top and bottom ones the same or different? Same, right? So I don't want to consider that now. So here's 3 options. This is only alkenes though, so let's do the same exercise with alkynes. So I can start with my triple bond on the end. Do I have to worry about E and Z with alkynes?
No.
No, right? I don't have 2 groups to compare. So that's one possibility. I could also have my triple bond in the middle. Same thing with my putting the triple bond on the other side. Are these 2 the same or different?
Same.
Same. So not considering that. So that's how I went through and just drew out options and said, where can the double bonds go? If you haven't tried the practice exam, there's one question that I'm trying to prepare you for with thinking about this, and it was a big problem last fall. Because it basically says, here, think about all the possibilities that you could have given this reaction, and then you had to narrow it down from there. So you had to kind of go through this process of considering, wait, what functional groups do I have, and where could those double bond or triple bonds be? And do I have ones that are end up making it the same compound or not? So if you drew this one and this one, right? Well, that's taking away a box, and now you've used the same answer twice. So recognizing when you have structures that are the same or different. If that's still hard for you, nomenclature. This would be a 1-butene. This would also be 1-butene. Right? So if you're still having trouble being able to rotate, like I said, that's where nomenclature I think is more valuable than having you actually answer questions on nomenclature. It just helps me see when things are the same or different.
Could you do also like, sort of like looking kind of like journal planner? Could you do that and put like a double on there? But it's like not on a straight line. Like
Which one of these are you thinking about?
just like if it was like 3 coming together in the middle. Does that make sense? Like
No.
like this. Could you do that?
That carbon backbone wouldn't match up here.
Okay.
So what she asked, I think, was that. If I hydrogenate, that's going to look like that. And that isn't, that's different from this. Does that make sense? So like, I like that you're thinking that, but if it doesn't give you that compound, then that can't work either.
So that's fine.
Yep. 5 possibilities. I wrote this question for an exam in another class, and I didn't want to make you have to think about cis and trans. That was the hard part here, I think. So I included those in both. So 5 possibilities for 4 boxes. I wouldn't be surprised if on your exam, Dr. Gano does something like this, where he might draw like 7 boxes and make you say draw as many as you can. Okay, so be careful that not the number of boxes might not be the exact same answer. He doesn't, I think, kind of giving you like saying 4 or saying 2, it kind of restricts you. So on the practice exams, you might see questions where it's like draw as many as you can, or you potentially use all the boxes. You might not need all the boxes. So be careful about that limiting you. I would really want to say like, hey, all 5 of these are definitely possible answers. Okay. From this week in discussion and last week too, actually, these starting material ones seem to be the biggest problem. And that's why I really wanted to kind of go through my thought processes and thinking functional groups, drawing at all the possibilities and narrowing it down from there. Okay, let's keep going. Mechanisms. I've seen this reaction be really problematic in discussion this week, so that's why I added it to this. If you go back in your notes, Dr. Gannon gave an example of this reaction way when we started chapter 5. And he said, think about this one, try and draw the curved arrow mechanism for it. So it's not the exact same question as what he showed in class, but I wanted to pick this one just to make sure everyone's comfortable with drawing the arrows for this one and making sure you can identify how this product was formed. So to get things started, I'm going to go ahead and use my Br2. My alkene is going to go ahead and attack either one of the bromines. I'm going to push electrons onto the other bromine. The biggest mistake I saw in problem solving this week was making a carbocation here. Remember that bromine has lone pairs. It's able to make a bond to both of the carbons in the alkene, thereby eliminating the carbocation intermediate and eliminating a structure where an atom doesn't have an octet. So Br2, we're going to make our bromonium ion intermediate. HBr, HCl, we add the H first. H doesn't have lone pairs, so we have to make the carbocation intermediate. So I saw a lot of work this week where I saw carbocations here. I would take off points for them. At this point, I have Br minus. That could attack, but I can see here that I don't have 2 bromines. That means that the oxygen that's here as the alcohol, that's what's serving as my nucleophile instead of water like we saw in Br2 with water addition. So we still have an oxygen-based nucleophile. Is this coming back? There was a homework one where you had to work backwards from this a few weeks ago now, but a lot of students asked me about that one, so I figured going forward would be another good example. At this point, my water needs to come in. I'm still going to use the water, and I'm still going to attack the more substituted position. So this carbon would be classified as a secondary. This carbon would be classified as a tertiary. So my water is going to come in, attack the tertiary position, pushing the electrons from the carbon-bromine bond onto the bromine. That gets rid of the positive charge on the bromine. For this, I saw a lot of students trying to deprotonate this oxygen, try to make it O-. In order to do that, we need a pretty strong base. Br- is not a strong base because its conjugate acid HBr is super strong. In other words, which atom is going to be happier with a negative charge? Br- or O-? Well, Br- is a weaker base, so it will be happier with that negative charge. The other thing I think about is that in this case, this bromine having a positive charge is a really big problem. So I don't really need a strong nucleophile in order to break that bond. That carbon-bromine bond is already really weak because carbon is already less electronegative than bromine to begin with. Bromine's more electron rich. And it's positively charged, so it's holding its electrons even tighter. So since it's positive, you actually could think of it as being more electronegative than it was when it's neutral. It really is holding on to the electrons it has because it can't afford to lose another one to become +2. So my hydrogen is going to stay there. My last step, I also am showing you HBr is formed. So I would want to show how I'm making both of these products. If I didn't show HBr and you wanted to use another molecule of Br-, if you wanted to use an alkene, like there's really no other option here. And the ones we did, if you want to use Br-, you want to use water, it's really a numbers game. But generally, if I'm asking for curved arrows, I want to be able to see how all the products are generated. So in this case, I would want to use my Br- to go ahead and grab that hydrogen, push electrons onto the oxygen, and that gives me my final product. So this was the one mechanism from chapter 5 that I had the most issues with this week. So I'm not saying this reaction is more important than others, but I had a question like this in discussion and I saw a lot of mistakes. So this would be one of the ones I would encourage everyone to review.
Water isn't shown, the error you're supposed to assume unless it says a different solvent. Because it also says Br2.
Yeah, so there's no water here. Water would be shown if it was included in the reaction. You wouldn't want water here because then the water could act as the nucleophile instead of the alcohol group here. So you don't want to have another nucleophile to compete there.
So then under what conditions would both of the PRs add to the
When you don't have another nucleophile present. It kind of goes back to 2070 or Gen Chem. Remember how when an atom loses an electron, it gets smaller because it's kind of holding on to those electrons even tighter. So we're saying that in this covalent bond, that carbon-bromine, the bromine already was more electronegative. Now it's going to hold its electrons even tighter to it because it doesn't want to lose those either. So it ends up actually increasing its electronegativity because it's holding on to its electrons tighter and it's smaller, so the bond's weaker.
Why is that important?
Why I'm showing you that why this can come in because too many students were taking this H off first. So the idea that this bromine is positively charged, the carbon-bromine bond very long because it's very weak, and so you don't need an O- to attack this position.
So I anticipate that a question like this would show up on an exam because like the two, not just one student, have any mechanisms.
I have seen other prelim 2s in 3570 have curved arrows. And I would say for me, maybe that's a bigger emphasis because I do think at some point on the exam, it might not be the entire, but something with curved arrows. And so I've been seeing a lot of strange curved arrows in the last week or so. So I think the easiest way to prepare that is to go through the entirety of one. But I have seen exams where this is a style question for Prelim 2.
Why isn't the oxygen generating its own pitch directly to the bromine rather than generating it to each other?
This bromine has 2 lone pairs, and so if the oxygen comes and adds to that bromine, then the bromine has 5 groups. And so you don't want to exceed that octet. That bromine is positive because it's missing a lone pair, not because it's missing a bond.
Right.
So carbocation, right, that's different. Carbocation, no octet, missing a bond. Well, we want to add that group to it. So just because an atom's positive doesn't mean it wants a new bond. You kind of already know this with H3O plus. Right? So when we use H3O plus, that oxygen is positive. It doesn't want a new bond. It wants to lose an H to get a lone pair back.
And also it breaks the BR breaks that bond as opposed to the other bond is because because
This position is more substituted than this. So this carbon is better equipped to help handle the positive charge that the bromine's feeling the burden. Okay. Last one, then I want to keep going. Okay.
Partially positive because the bromine is like turning to some oxygen.
Yep.
And that's why the oxygen.
So it actually is doing it to both carbons, but the bottom carbon is feeling is greater positive because it's more substituted. So like I would say like 80% of that positive is on the bromine, but of the other 20, a lot more is on the more substituted position than the other. Okay, chairs. So I did do a lot of practice and discussion today with chairs. It seemed to go really well for students or really poorly. So if you haven't watched the chair video, I try to give you a specific procedure that will apply to every chair question with some examples. So I might go through this a little quickly, but I encourage you, if you're still stuck on chairs, to check out my video. And also, your homework that's due next Friday after the exam has good chair practice questions on it. So I'd encourage you to try those this weekend because you're going to have to get them done anyway, and they will help you on the exam. The homework that's due next Friday has some reaction questions. If you see any reaction questions, I wouldn't worry about those until after the prelim. You'll see what I mean tomorrow and lecture on Monday. But I do think doing the Chapter 7 homework should be on your priority list before the exam so you can get more chair practice. Okay? So for this one, you have a couple different options. You should be able to recognize what this chair looks like or what this structure looks like. But if you want to go ahead and draw it, I know that when I'm trans, I have one of those groups pointing up, one of those groups pointing down. It doesn't matter which one is pointing up and down. That's all about perspective. So this would be a possible structure that I would draw. My ethyl group here is on a wedge, so that's coming up towards me. My isopropyl group is on a dash, that's going away from me. That means it's going to end up pointing down. So now at this point, in the video I talked about my template here to help me keep track of which carbons are which when I do my flips. I would go ahead and say, well, the way this is named, ethyl's carbon 1, let me go ahead and add that ethyl group to carbon 1, and I'm going to want to add it based off of the perspective that's being drawn. So because that ethyl group I've drawn is coming towards me, that's going to be on the up bond on position 1. That means I'm going to go ahead to position 1 and draw it on the axial spot. Now, position 2. I'm going to follow my template here. Carbon 2 is up at this spot. The figure I took this book from went counterclockwise. You can also go clockwise. That's totally arbitrary. And I'm just using these as placeholders to make sure I know which carbon is which when I do my flip. Now I'm going to go ahead to carbon 2. At carbon 2, I can see that this isopropyl group is on a dash. So this is going to go on the down bond. So I look at carbon 2. The down bond is the axial bond. So I'm going to draw that going down. Now when I do my flip, remember that carbon 1 is at the top here. It goes down to the bottom in my flip. The reason why the dash and the wedge is so important is that that tells us direction And direction does not change when we do our ring flip. So the fact that my ethyl group here is pointing up, I need to have that also pointing up in my flip. So my up axial bond flips to my up equatorial bond. And that's why I think keeping track of your carbons makes it really easy to see that, because if you know where carbon 1 is, there's only one way that equatorial bond can be drawn. It has to be pointing up here. If you pick a different carbon, right, say you wanted to move it to this position, well, the bond that's up there is still axial. You didn't flip from axial to equatorial. So it does matter where you put that group. That means that at carbon 1, my ethyl group is going to be up equatorial. I know that this is up here because my axial bond is pointing straight down at that position. Now I'm going to again go to carbon 2. So at carbon 2, that group is pointed down axial. In my flip, it's now going to be down equatorial. At carbon 2, my equatorial group is down. Perfect. So I ran out of space a little bit there. You don't have to draw it in a weird angle, right? But make sure you have the correct number of carbons. Now circle the more stable conformation and have 2 axial groups versus 2 equatorial groups. The more equatorial groups is going to win. Yep. As long as, oh yeah, that's fine. They're still going to be both equatorial. Though if your structure looks different, the only thing that matters is that the position you pick those substituents to be on, your bonds match my axial and equatorial bonds. Meaning, if you didn't want to put your number 1 here, you wanted your number 1 here, make sure that whether you picked up or down, those bonds match this template. So if you were at carbon 3 and you wanted to make that your ethyl group, you can't decide that that axial bond is pointing down. At carbon 3, the axial bond is pointing straight up. So that template tells you the direction of where bonds are at that specific carbon, and you cannot change those. But you can change where on your ring you put those groups. Okay? I think it's easier to always put one group at the same position, because then you'll get used to seeing your axial and equatorial bonds, and you won't have to worry about flipping them. So in every chair question I ever do, I always put a substituent in that upper right position. So that way I know where my axial and equatorial bonds have to be. But you don't have to do that.
Do we know that the one is the wedge and the dash, one has to be one and the other because it's strands?
Correct. But it doesn't matter which one's which. Right?
So if it was cis, they both be wedge or both be wedge.
Either one, same idea. Okay? So be careful. A lot of students make the mistake of, oh, if it's strands, that means one axial, one equatorial. It only means direction. Okay? So a lot more practice. I'm going to keep going. I'm already going to go a little over. So if you guys have questions about this one, I'll come back to it. A lot of practice. I also have extra copies from discussion with more chair. So don't everyone get up right now. But if you didn't come to discussion and you want to try more chair questions, there's extra sheets there. And the video will be up tomorrow morning with the solutions. 9, this was one of the recommended textbook problems, just to get more practice being able to convert from a planar structure to a chair structure. So I like having to go backwards here. So just making sure I can see that my top equatorial bond is pointing down. I'd want that group to be on a dash. This bottom equatorial group is pointing up. I'd want that to be on a wedge. So it would look something like this. Again, the position of those groups doesn't matter. It just makes sure you need to have one up, one down bond. I think this came up on the last exam too. So if I say planar like this, right, you're going to want to draw these flat. Our chair structure is kind of looking at it sideways. Next one, same thing here. So I have another chair 6-member ring. Both of these bonds are pointing up. So I should have a methyl group coming towards me, an ethyl group coming towards me. So those should both be coming out of the board. So on a wedge. This last one is a little tricky, but remember the other group that's on this position, right? If this equatorial or bond is pointing up here, my other group's going to be pointing down. So actually, sorry, I said that. This is my axial group here. My other equatorial bond is going to be pointed down here. So that's where that hydrogen is. So my hydrogen's pointing down. So is this OMe group. Those should both be coming away from you. This is an example of the cis and trans rings that came up yesterday in lecture. So I wanted to at least give one example. I think this is straight from one of the recommended textbook problems. I can't remember what number, probably one of the high numbers. But so if you haven't seen an example style like that, that's where I'm getting this question from. It's definitely on the list for Dr. Dan. Just a quick.
In that dashed H would have lost its flux, correct?
Yeah, because that H could be either going up or down. And so being able to say that this bond, like drawn in that H there, you'll definitely see that it's down equatorial. Yeah. Keep going. So just more products. So this one is already talked about the mechanism for this one. So making sure that here I see water, bromine's going to go to the less substituted position. Water is going to go to the more substituted position and get deprotonated in that last step. In this case, you could imagine either the water or the Br- was taking that H. It's a numbers game with water being a solvent. So water probably is doing it, but it's no way for us to tell. Next one, it's been a while for this. This is a chapter 4 reaction. And remember, this goes through a carbocation intermediate. So I'm going to add the H. Remember Markovnikov's rule, that H is going to go to the position with more H's. We're going to end up making this intermediate. It's been a while. We don't really talk about carbocation intermediates in chapter 5. And so why I threw this one in here, this is a secondary carbocation with a tertiary position right next door. This is a hydride shift question. Very common exam question. All right, so it's been a while from chapter 4. I tripped a couple of students this week with this style question, but this is not going to add the bromine here. We're going to do our shift for our arrows. If I have time, I have the example of a mechanism where we're doing a shift, so I'll show the curved arrows for it. But what we're going to end up with is the carbocation on the tertiary position. That's where the bromine's going to add. Bottom one. Is this Markovnikov or anti-Markovnikov reaction?
Markovnikov.
This is Markovnikov, so I need to go to the more substituted position. But in this alkyne, both of these positions are equally substituted. So I end up making two different products. I could have the double bond oxygen on the alkyne carbon on the left. I could also have the double bond oxygen on the alkyne carbon to the right. And so I have, in this one, I have my double bond oxygen on carbon 3. In this one, I have the double bond oxygen on carbon 2. So we have two different products here because both positions in my alkyne are equally substituted. If one of them was more substituted than the other, then I would only get one product. Next one, ozonolysis. So I threw this one in here. This one probably, I think this is the first case where you saw it where it had two double bonds. It doesn't react any differently, but we now have to make two cuts instead of one. So what I'd encourage you to do is label these with your numbers. And what that means is that 3 and 8 are going to no longer be connected. 1 and 9 are going to no longer be connected. But the rest of these carbons are still going to be connected. So by making those two cuts, do I have two molecules as a product or only one? Only one here. 3 and 8 are no longer connected. 1 and 9 are no longer connected, but 8 and 9 are, and 1 and 2 are. So we're going to have a really long chain. Now let's go ahead and make sure I have every carbon accounted for in my product. So at this position, this is going to be the aldehyde. What carbon does this have to be? Does carbon 3 have an H? No H on 3. Does carbon 8 have an H? So that's got to be either 1 or 9. I can see here these two carbons have both carbonyls. Those have to be next door to each other. So that's 8 and 9. That means this has to be 1. Easier way to see that, right? 1's going to get a double bond O. 1's still going to be connected to 2. 3 is still going to be connected to 2. That's also where we're going to have a double bond oxygen. I think that one's almost impossible if you don't number your carbons. Next one, we have here oxymercuration. Oxymercuration, remember the M in oxymercuration should also help you think Markovnikov. So more substituted position. That means we're going to end up having the OH to the more substituted position in my alkene. We kind of already talked about this one. Remember, this only works for alkynes. And so it's not going to touch the alkene. It's going to reduce the alkyne to an alkene. But it also is going to reduce it stereospecifically, meaning we're going to make that alkyne into the cis alkene. That's another one. If that feels like it's been a while, that was chapter 4. So Lindlars with alkynes make cis alkenes. In the other example where we used Lindlars, it was a terminal position. Cis and trans wasn't possible. So if you have the possibility of being E or Z or cis or trans, it will make the cis one. If it's on the N position where you have two of the same groups, you're not going to have E or Z or cis or trans. Notice the alkene here isn't touched because this is an alkyne reaction conditions. I wanted to go through the rearrangement just as a refresher, but we did talk about this a few times. We did do this in discussion. It's just been a while. In order to get started, let's go ahead and use our alkene, go out and grab the hydrogen, push electrons onto the bromine. In this case, these are equally substituted. So doesn't matter where I put the positive charge. You could put it on the left carbon, you could put it on the right carbon. Those would be equal. I'm going to go ahead and put it on the left carbon. Now at this point, I can see here in my product that the carbon where the bromine is no longer has a hydrogen. So that's a nice indicator that the hydrogen that's at that position has to move. So how I would show that, I'm going to circle that H. I'm going to start my arrow at the bond, and I'm going to point to the position where those electrons are going. This allows me to go from a secondary carbocation to a tertiary. Now I can see how the bromine gets to that position. So my Br minus can come get added, and I get my product. Going from a secondary to a tertiary is not the only way we see rearrangements, but it's by far the most common. So my advice, now that chapter 4 has been so long in the rearview mirror, if you make a carbocation, before you add your nucleophile, make sure there's not a tertiary or quaternary position next door. If it's a tertiary position, you could shift a hydrogen. If it's a quaternary position, you could shift the methyl or an alkyl group. Okay, but if you really kind of want to focus on major things, I would say I'd be very surprised if you didn't have a question where it dealt with a rearrangement. That's a very common Prelim 2 question. If that feels strange, on one of the practice exams, Prelim 1, there was a red predict products question. You might remember you didn't have to worry about it. One of those was a rearrangement question. So go back and check the practice Prelim 1s for any predict products questions, because we didn't know any reactions for your Prelim 1, but one of those did have it on there. Does everyone okay what I mean by that? Mm-hmm. Okay, so go back to the practice Prelim 1s and see if anything's in red that wasn't on Prelim 1, it's on your Prelim 2. Okay? Just to give some other examples to make sure that you have predicting products practice we did tonight, providing reagents, and predicting starting materials. So any one of those three can come up. Usually Prelims 2 have a mixture of all three of those. In this case, I have an alkene. I end up making a dihalide. A bromine went to each position in my alkene. So this is an HBr. This is Br2. This would also go through the bromonium ion. Br minus would come in and attack. Next one is this Markovnikov or anti-Markovnikov addition. Anti, that's hydroboration. Another good prelim 1 topic. Anti-Markovnikov, right? I would be surprised if you didn't have to do hydroboration of alkenes or hydroboration of alkynes on the exam somewhere, right? It's kind of a, you probably know by now from Cornell in 2070, right? We kind of like to focus on those exceptions, make sure you know them. Right now, those are the only two anti-Markovnikov reactions we know. So I'd be surprised if one of them wasn't on there. Last one here, I've added 2 bromines to the same position. This is my alkyne reaction. In order to do this, I'm going to need HBr excess. My less substituted carbon got 2 H's, so that's why I have a CH here that's turned into a CH3. So this carbon on the end here has 1 hydrogen. This carbon now has 3 hydrogens. This carbon had a triple bond. It now is still connected to 2 carbons. The 2 pi bonds went, and then we added bromines with those. Okay.